In this video, we're going to talk about how interactions work within the context of linear regression. So, taking a step back, many machine learning algorithms that we have access to can find some interactions on their own. Things like decision trees, for example, are notorious for being able to figure out interaction effects, and that, in some sense, that's really all they do. They're just looking at, well, within this variable, look at its two child nodes, or within this variable, what can we split it on again? So that's, again, an interaction there. However, there are some algorithms that can't. Beyond that, it does take effort for your algorithm to find those interactions. That means that it has less of its resources available in order to find other things that are interesting or useful. As a domain expert, or as someone with contact with a domain expert, you might be able to find some interactions that make sense to explore that an algorithm wouldn't because it doesn't know what's worth checking. Theoretically, you could just go in and plug in every possible interaction effect. Multiply every variable times every other variable. Now you've squared your number of variables, and wow, you can have a great, much better model. But it's not actually a great, much better model. It's a wildly overfit model because you've just created a whole bunch of different patterns that don't really mean anything that your algorithm can pick up on to distinguish different things. So using domain expertise allows you to select useful interactions and only consider those. Finally, interaction effects are useful in trying to handle how different variables are correlated, or handle when variables are highly correlated with one another. So, let's go over an example of an interaction effect. It's been said that therapy and medication work better together than either would on their own. If you have a simple model without an interaction effect, you can get something like mood is equal to 20 plus 2.5 times drug plus 5 times therapy. So, the more of a drug you take, the better it works, or the better your mood is. The more therapy you do, the better your mood is. I would assume that both of these are coded as 0, 1, or something like that, instead of just scaling freely. You can now check an interaction effect to see how that would compare. So now we've got 20, we have our same intercept, our same base rate, or our same prediction for someone who was on no drugs and not in therapy. And then we have 2.1 times drug, plus 4 times therapy, plus 1.5 times drug times therapy. Now, drug is a little bit smaller, so we're seeing the effect of drug is smaller. Therapy is a little bit smaller. The effect of that is diminished as well. Why are they diminished? Because some of what there was in the simple model that was for drug or therapy really should have belonged to their interaction. So now that we've pulled it out separately and put it on the end, that decreases the magnitude that either drug or therapy, or the magnitude of the effect that either drug or therapy have on their own. However, we still note drug is still pretty positive. Therapy is still pretty positive. Drug and therapy, even stronger when used in combination. If we are going with dummy coding in this example, so 0 if you didn't take a drug, 0 if you weren't in therapy, 1 if you did take the drug, 1 if you were in therapy, the interaction effect would go away unless you were in both. Because, there'd be a multiplication by 0 in there. And that would lead to a situation where your prediction of what your mood would be lower if you were just in one of them than it would have been in the previous model. So let's say you were taking a drug but not in therapy in this model. So that would be 20 plus 2.5 times 1 plus 5 times 0. Goes away, so your prediction is 22.5. But down here, same situation, is 20 plus 2.1 times 1 plus 0 for the rest of these. Your prediction is now 22.1 instead. So not only does it disentangle a little bit, yes, some of the effects of drug and therapy that we're observing are a result of them being together, but it also lets us say when one of them is absent, or when everything is absent, what can happen. The next thing I want to note is that interaction effects work just as well for continuous variables as they do for categorical ones. You could absolutely multiply age times fair instead of multiplying sex times p-class. Because in regression you have to convert everything to numeric anyway, they also work between continuous and categorical. So we've got a situation where you can have age continuous times sex. For purposes of how it's coded on the Titanic project, is binary. But you can multiply any combination of continuous and categorical because they're all being turned to numbers.